This is Devdipta Goswami. I am a postdoctoral research associate at Princeton University working with Dr. Clancy Rowley. Thanks for stopping by my poster. My research is broadly based on data-driven identification and control of complex systems with guaranteed performance. My research objective is to understand the safety critical control of next generation large scale autonomous system by exploring the interconnections among the domains of data-driven modeling of dynamical systems, control theory, mathematical optimization, and cyber-physical systems. My intended research program is motivated by the deluge of large-scale automated systems that are going to wrap our daily lives around. For example, the use of drones for package delivery, search and rescue, and the proliferation of self-driving vehicles and the connection between softwares and physical systems. The traditional analytical methods are too simple to reliably model them, but the improvements in sensor technology and computational power leave us with a lot of data and the data processing capability to leverage it. My research program has three basic thrusts. First is the data-driven identification, estimation, and controller synthesis, where my goal is to identify a complex model from data and design a controller based on that model. We can use several methods here. One of the methods that we have tried is the linear identification through the infinite dimensional Koopman operator spectra. And we also tried the neural network based identification. Koopman operator is an infinite dimensional operator that operates on a space of observables. And this gives us a very nice systematic approach to identify a nonlinear system from data through extended dynamic mode decomposition and its sister algorithms. Now, in my PhD research, I have used extended dynamic mode decomposition from the data to identify a nice bilinear form from a control affine nonlinear system. And we have also proved that if there exists a non-recurrent set in the original dynamics, the Koopman bilinear form is actually convergent. And we have synthesized an optimal control using the Pontryagin principle from this Koopman bilinear form. But the problem that kind of plagues this Koopman-based approach is the choice of the dictionary function. Because we have to work in the Koopman invariant subspace on which we identify our dynamical systems, we need to have a dictionary of observables on which we kind of approximate our Koopman operator. And there is no way we can make sure that, like a priori, that we have a Koopman invariant subspace. On the other hand, we can use the neural network, which has the universal approximator property to model any dynamics. Here we have used an ecostate network, which is a very special kind of neural network where only the output weights are trained, so it can be trained very cheaply and fast. So our proposed method uses an ensemble Kalman filter to recursively assimilate the new sensor data that are coming in, while in the training phase, the ecostate neural network is modeled with all the available data for the training period. We have used this ecostate network augmented with ensemble Kalman filter for the traffic flow prediction in vehicular networks, and it turns out that it works pretty well if there is some sort of periodicity or some sort of regularity in the data. The future objective is to use these neural networks for the dictionary creation of for the Koopman mode identifications. The main problem for the Koopman based model identification was the creation of the Koopman invariant subspace from the set of observables, and we can use the neural network to automatically create the dictionary there. And we can also use the model predictive control on the model that we identify through the Koopman based methods, more specifically the Koopman bilinear form. The second thrust of my research program is more application based. It's on the multi-robot swarm and the large-scale autonomy using the multi-agent systems. The goal of the project is to use the multi-agent system, more specifically drones, for autonomous target tracking in an uncertain environment. This is very useful for autonomous search and rescue in an uncertain environment and has a potential military applications. The methods that we have used is the probabilistic environment mapping using an occupancy graph. So we have this environment and we divide the environment with nodes, and each node has certain state, like either it's occupied by a target or it's not occupied, or it's a void node, which means the target cannot go there. Like that can be a like a building in a vehicular road system where a vehicle cannot go. So that will be a void node. And then we have modeled it using we have modeled the target's motion using a biased random walk model. And we have used the mapping of the environment using a method that maximizes the mutual information between the target info and the info whether a node is void or a legitimate node where a target can actually exist. So this kind of environment exploration actually performs better than a naive random walk or naive randomized exploration model or a lawnmower algorithm. In future, we are planning to use the sampling-based motion planning or probabilistic inference, and also reinforcement learning for task-based UAV operation. The third part of my intended research program is coming from my current work at Princeton University. It's about safe control of a system while learning on the fly. The goal of this project is controlling a system while simultaneously learning its unknown parameter. The motivation of this project comes from several scenarios where a certain change in environment or some breakdown in the system changed its dynamics, and that dynamics has to be learned on the fly while controlling the system, because the system is already deployed in the field and we cannot really stop its control and gather trajectory data and learn it. This is very interesting because a lot of time when an aeroplane gets damaged, the human pilots are a lot of time they can manage to safely land it, but this is probably an unlikely feat for a present day autopilot. But the long-term goal of this project is to design such an autopilot that can perform this kind of safe control of a system while simultaneously learning the changed dynamics. We approach the problem in a minimax Bayesian setting where we devise a strategy, control strategy for the system where we don't know certain parameters in the system, where we have an adversary who has the exact knowledge of the system and generates and gives a strategy which incurs the optimal cost. Now, due due to our ignorance of the parameter, we will incur certain cost, will and that will be more than the optimal cost. So we will incur certain penalty, which we call regret here. The regret can be either multiplicative or additive, and we want to minimize the worst case regret. So the parameters then can be chosen adversarially by an adversary. This is a very challenging problem to solve because a lot of time, even for a simple system like an LQR system, this problem becomes more like solving a very high dimensional PDE. And that's computationally challenging. We are trying to find out more computationally feasible algorithms that will generate a regret that's within a certain bound of the optimal worst case regret. So these are my principal research thrusts that I'm planning to bring when planning to bring into the table when um, I am when I join as a faculty, and we got a bunch of publications out of these research trusts, in, including IEEE Transactions and Automatic Control, American Control Conference, IEEE Robotics and Automation Letters, IEEE Control Systems Magazines, and IEEE um, Conference on Decision and Control. So thanks a lot for coming to my poster presentation. And if you have any question, please feel free to reach me at goswamid@princeton.edu. That is goswamid@princeton.edu. Thank you very much, and I'll be open to any questions.